Welcome to the Cosmic Pie Podcast, Episode 12, Season 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota.
Indeed.
Grand Forks, North Dakota, where spring has sprung.
Something like that. Yeah. Of course, I'm looking at Thursday night when I'll have to be out at the telescopes for our first student observation of the semester for the Space Studies Department. And here we've been in 40s all week, and it's going to be in the 20s on Thursday.
Well, just compared to what it was like in January.
Oh, yeah.
It was a minus
Much
20s.
better now.
Just think of that when you feel a little cold,
little salty.
You're shivering a little bit. But yeah, it's beautiful weather around
is.
here. Now, today we actually hit a high, I noticed, of like 50 degrees
Right.
Fahrenheit, 10 degrees Celsius. So beautiful weather.
Yep.
The grass will soon be up.
Yep.
And it's really, really nice.
Turning
And
green from the
From the
nice
dead-
beigeish brown.
the dead gray, the
Yeah.
dead brown that you get. Yeah, it's getting there.
Yep.
We do have a live chat feature that's running, so if you have any questions or comments, please use that. We don't get many questions that we'd like to have a lot more. So if there's something out there, like,
And,
you
we
know,
might, and I don't know, we might not get to all of them, but we do still appreciate them. So.
yeah, we definitely like, and we'll stop what we're gabbing on and
Yeah, I'll
try
try
to
to. Yeah.
answer the questions. The other thing is disclaimer, Robert. You usually do that. You want to do that again?
Okay, sure, why not?
You're not tired yet?
Not yet. Maybe someday.
That's
Anyway.
that's a disclaimer. Right? You're tired.
Yeah. So the opinions and all that expressed herein are those of myself and Wayne, not those of the Department of Physics and Astrophysics, the College of Arts and Sciences, UND in general. It's just us. You'll have to come at us.
Now, for those who are wondering, we do upload our podcast the next day to Spotify. So if you're ready to listen to it on Spotify, or you want to listen to it twice, or even 3 times,
Hey.
or more, it's there. You may not catch everything, in the first listening.
Right.
The other thing too is that if you have any suggestions of topics that
Yeah.
you'd like us to cover,
Comment.
yeah, let us know. I mean, we will do the best we can. We kind of use this. We'll have guests. In fact, at the end of the podcast today, we'll mention about a guest coming up on April the 7th. And we tried to get other guests. And then in between times, as you notice, we talk about sort of current events, what's happening in the latest news related to astronomy, physics, and so on. But if there's anything out there that you would like us to cover, or at least have our opinions on various things, please let us know.
As other YouTubers say, comment, like, and subscribe.
Yes, make sure you like. So please give us a thumbs up. And that's how we know that at least somebody enjoys the podcast.
Right.
Because if no one likes it and everybody hates us, you know what happens?
We quit.
It,
Eventually, anyway.
it goes away.
Yeah.
Anyways, so the first thing I want to talk about, Robert, is did you get a chance yet to see the movie Project Hail Mary?
I have not. So, what about it? Because
Well, if you want to go back to the main screen, I should have
Okay.
shown this first. Just to prove to you that I have read the book. Here is the book. It's not
Nice.
like capital the book. That would
Right.
be like the Bible or
something
right?
like that, yeah.
But this is Project Hail Mary. I read it back in the wintertime, so a couple months ago. And usually I don't do that, but I heard that the book was made into a movie that would be here opening up around March the 20th. So I went ahead and read the book ahead of time. And of course, the author is Andy Weir, the same person who wrote the book The Martian.
Mm-hmm.
And a lot of people have seen that movie.
I've seen that movie and read that book. I haven't read this one yet.
And you haven't seen the movie?
And I have not seen the movie.
Haven't seen the movie yet. Now, sometimes we can go to the slide
Okay.
to kind of advertise.
Sorry.
Sometimes, you read a book either before or after a movie, and then you make the comparison. It's just natural, of course, with the movie itself. And say, the book was better, or maybe the movie was better. It's usually the book is better, maybe it's a little bit, you can address this as an author. Maybe it's because when I read the book, it's better on my brain in the sense I can visualize to myself what's going on. And sometimes the way I visualize things or think of a way that things are happening, the scenery and stuff, is not what, of course, Hollywood or someone else would come up with.
And, sorry, my view is, because I've stopped trying to make that comparison, as long as the movie that is an adaptation movie is still telling that story from the book, I'm usually okay with it now, because a book is not a movie, and a movie is not a book. With a movie, you've got 2 hours to tell that story. Things got to pop, things got to move. In a book, I can take a few pages to give you the internal monologue of the character. I can present more details and things like that. So a book is always going to seem to certain people better. But a movie is going to seem better to others because it has that pop, that snap. And I got to admit, I get kind of annoyed when nowadays people are wanting books to be like movies. And it's like, if you want a movie, go watch the movie. You know?
Well, reading the book, you get to use your imagination.
Right.
When you're watching a movie, you can cut that part off because that movie's providing you with the visual scenes.
Right.
So it's a different experience altogether. We'll just put it that way.
Absolutely.
And for this particular movie, the book follows and the movie follow pretty closely. There's only one. I'm not going to spoil it in case people haven't seen it. There's only one part near the very end that kind of deviates a little bit.
Yeah.
From the book, the movie does. And that's because they add in a little extra information to kind of close up the loop in some sense, right? Of the storyline itself.
And you do that in a movie. Yeah.
And so I could understand why it's there. But as far as everything else it was concerned in the movie,
Well, his other book, one of his other books, the Martian, the movie is a good adaptation of the book. It's pretty much that same story. They just cut out a lot of the things that went wrong on poor Mark Watney. So I'm figuring the same thing happened here.
Actually, I read the Martian book as well, but I read it after the movie.
Yeah.
And I find that this book, Project Hail Mary, was actually closer to the movie than the Martian movie in the book. So there's a closer link.
We discussed The Martian a few days ago, and how the final scene is just, as a physicist, you got to kind of sit there and start giggling and going, oh, no, they did not.
What? How come when you say The Martian, I always think of that character from Looney Tunes?
Oh. Where is my Umodium Q38 space modulator?
I think we just gave away our age.
Probably.
But one of the kind of interesting thing with the Project Hail Mary is the connection with extraterrestrial life.
Yeah.
How do you communicate with life from another planet? And it's not going to be, hi, how you doing? You raise your hand. Because maybe raising your hand and waving it to someone in a friendly gesture is a way that you would do just before you killed somebody on their home planet.
Right.
So you got to be very careful of interpretation.
Mm-hmm. Well, let me ask you this. How do you know they have eyes?
Well, that's another thing. How do you know they have ears?
How do you know they have ears?
So how do they sense their environment? In fact, that's kind of like the movie. Like I said, I'm not going to give it away. But the life form that the astronaut runs into, it doesn't have eyes like we have eyes.
Right.
They sense things sort of in waves, like in sound.
Mm-hmm.
So that's interesting how Andy Weir went about figuring out ways to communicate with a life form then that really only senses sound waves in that sense. What would you do?
What would you do?
And one of the things that, I guess I am giving it away a little bit, but one of the things you do is he had a laptop set up where you think it's saying something like no, yes, simple sort of responses, and recording the sound, and then the waveform of the sound that means in English, yes. So anytime the computer through a microphone hears that waveform, it would automatically display on a screen, yes.
Okay.
And afterwards, after a while, of course, you can build up the vocabulary.
Right.
So then you're getting simple sentences sort of thing at that point, and then can, the mediocre sort of communications.
And extra bullet is putting up something that has been felt to be the truth. Mathematics is the universal language. And to a degree, I agree with that because pi is coded into the universe itself. E, Euler's number, coded into the universe.
Right, and that's true, but you still have to express numbers to a life form.
I agree.
I mean, you can't, you can hold up one finger, but what does that mean?
Right.
And you could count. I guess you could move objects around and put one object, let's say, in one place and hold up your finger as give a sign of 1, and then move a second object and give a 2, and then 3. Then they would get the counting that way. So I'm sure if you work on it long enough, you'll get it.
Right.
And that's kind of the argument that people made way back when they sent, the plaque on the Pioneer spacecraft and they sent them on the Voyager spacecraft. How do you know that if any civilization, advanced civilization, finds the Voyager spacecraft, let's say, in the distant future, and they look at the golden disk, the record that's on it, do you know they're going to be able to figure out most of the information that we think is there to be looked at? You know what I'm saying, right?
And we've had the same discussion, that we as in general, about storing our nuclear waste. Because how well can you read Egyptian hieroglyphics?
Yeah, and that's kind of what it would be like, 10,000 years from now, if depending on the radioactive material, it's still very potent.
Mm-hmm. Yeah.
What kind of universal sign do you put on that area to warn people? You know what it reminds me of in that sense?
Yeah.
I just thought about it. It's like the Alien movie.
Yeah.
Right? So they broadcast out a signal which caught the attention of the people that were transporting like iron ore or something from one location back to the Earth. And the computer heard the signal while they're in hibernation.
Right, and steered them toward it.
And thought it was an SOS. Mm-hmm. And so it was under contract that if they pick up any kind of signal from an intelligent life form, that they had to go and investigate or something like that. And it was after a while when they analyzed it in detail that they realized it was a warning message, stay away. Well, if you do have a situation like that and you want people to stay away, maybe it's better not to broadcast at all.
Right. Well, I've often made the argument that we don't really need to put up any signs. Because if they're advanced as we are, they probably know about Geiger counters and know, oh, hey, we need to stay away from there. And if they're not, if we've nuked ourselves back to the Stone Age or something, Gronk goes over there, comes back, hair falls out. Don't go over there.
Well, I mean, how do you know it's safe to eat blueberries?
Right.
And extend that backwards in time. There must have been some individual
who ate blueberries
and never died. And there are others who ate other berries that are poisonous and they didn't live very long.
There you go.
And so not to eat that. I mean, somebody has to do that first, right?
Yep.
So there's always that when you think about it.
I mean, we're laughing about somebody dying, but the scenario
Well, this person
is
technically
amusing.
would have died like many thousands of years ago. So it's not like,
It's not like we took somebody out who, would still be lingering around.
Well, given how many other people have died since that time.
Yeah.
You think of it that way, right?
A few billion, right?
Yeah. But anyways, so Extra Bulla mentioned that he said, I heard that the movie is really good. It is really good.
Okay.
Really good. In some sense, I wish I would have read the book after the movie because I knew what was happening. Once I realized the book and the movie were really close,
Right.
It spoiled it for me in a sense.
Okay.
Right? Because I knew what was coming.
And I'm one of the few people on the face of the earth that apparently does not mind spoilers.
Okay.
Yeah. So.
But yeah, it kind of spoiled
I'm a
it for
weirdo.
me. If it wouldn't have been, I guess, like the book itself, then it would have been different and it wouldn't have spoiled it, but it kind of spoiled it for me. And the best part of it is I got to go with Robert after the movie was over.
Uh-huh.
I got to go to Casa Mexico and have a chimichanga. Yum, 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 yum. That's Robert and I's favorite watering hole where we go and
They've got
suck back
some
to Mexican
really great
food.
fajitas, really great chimichanga. Heck, if you're ever in Grand Forks or East Grand Forks, as the case may be, Casa Mexico. Yeah.
A thumbs up to Omar for finding that place for me many years ago.
All right.
Great place. Now, the other thing, the latest news, of course, is update everybody, since we talked about it a lot, is what's going on with the Artemis II mission. So the Artemis, the rocket, was rolled back out to the launch pad at the end of last week. So it was going to go late Thursday evening, which it did. It was actually Friday morning at the Kennedy Space Center time, but who's counting? And so it has now been on the launch pad since Friday. And the expected launch dates, then the very first one, is April Fool's Day. Now, Robert.
Yes.
If I told you that you were going to ride in a rocket that has about 7.5 million pounds of thrust, built by the lowest bidder to the government, and we're going to launch you on April Fool's Day, would you go? Now, don't think too hard, Robert. Now, come on.
Yeah, probably not. But I wouldn't be offered the chance. My lungs are just too bad.
Well, the chance of actually going on April 1st is probably not great.
Right.
Just from historical launches, right?
Yep.
Especially one which is the first launch of the rocket that has people on board. We've launched it once before, unmanned it, couple years back, but this is the first time with actual people, so everybody's going to be play it safe, of course. Everything's got to be ready to go perfectly before they're going to push the button and let it go, or the computer's going to do its thing. So whether it goes up on April 1st or not, I'd be a little bit surprised, probably a little bit later, but we have a window that's open till about April the 6th, and then there's another date in the end of the month, April 30th, and that's just get to the timing right in terms of which part of the moon is in sunshine and so on.
Right.
And so there are priorities of when you want to go. And that's kind of where the windows are dictated. And of course, every month has a range of windows that you can go. So if you miss the April launch due to some kind of technical issue. And of course, the weather could be crappy on April 1st, right? I mean,
now
that
this
does a
is
lot
Florida,
to it.
so I got to admit, getting into May, June, July, you've got other concerns that start popping up, hurricanes.
Yeah, well, even just thunderstorms, right?
Right.
All this stuff can have a problem, or the wind is too high, and these kind of things. So there are issues you have to worry about besides technical issues with the rocket.
So I'm hoping they go in this window in April because
It would be nice.
And
the other thing is, NASA released information. I think this would have been yesterday or early this morning about the long-range plans for NASA's space program, and included things like the manned space program.
Right.
So they talked about things like the James Webb Space Telescope, the Roman Space Telescope, which is going to be launched later this year, most likely, and other missions that are ongoing or in the planning stage or whatever. They also included words. Now, these are words, and words are cheap.
Words are cheap.
Changing the words and the converting the words into actual physical labor and actually doing something is extremely expensive. But there were a lot of words from NASA today about building a lunar base, a permanently human-occupied base on the moon. Moon Base Alpha. It is coming, according to NASA. Now, this is the first time I've actually seen a lot of this coming from NASA as not lofty dreams somewhere decades from now, but actually stuff that we're going to work on here and now. And leading the way, of course, is the Artemis missions.
Yeah.
So that's what NASA's looking at, actually going back to the moon to stay.
Well, we had James Owens on a previous show come in. He's part of a team that's been working on space habitations. And so it's not surprising to me. People have been gearing up for just that for at least a decade now. But will it actually happen? Like Extra Bull is saying, yeah, when will Elvis get here?
Well, that's it, right? A lot of this depends, depends on the funding.
Right.
And the funding can change from one administration, priorities change from one administration to another.
Yes.
And that's the negative side of things.
Right.
Is that it would be nice if both sides of the aisle, as we say, could come together as a joint sort of statement to say this is the long-range plans for the next 20, 30, 40, 50 years. This is what we'd like to do. We've all agreed that this is a worthwhile endeavor.
Right.
So we are going to cough up the money
And we're going to make it
that
happen.
will support it, rather than switching back and forth, right? Depending on who runs the White House at the time.
Well,
or who
whoever's in
runs
the White
Congress.
House wants to be able to say, look what I did.
But that's the bad way of doing things.
It
That
is.
takes
It's
so
horrible.
much time to do, right?
Right.
I mean, just think of let's say today we decided we're going to build, an aircraft carrier. How long does it take to build one from the day we say, okay, let's decide to build that aircraft carrier, Robert. Let's go ask Congress for money. Okay?
Yeah.
How long does it take before that aircraft carrier then, is out there?
On the
right?
order of 5 years, I think it is.
Yeah, so that's more than one administration, you see.
Right.
So you're going to have, multiple administrations agreeing that that's a worthwhile endeavor, or someone will come along and cancel it when
Right.
it's, 70% built. And we've done that in the space program. Supposedly there are warehouses full of unused space equipment where somebody said, yes, let's do this, built it partially, and then the next administration goes and said, no, shut it down. And what do you
Right.
do with that equipment? You go and store it somewhere, you see.
Right.
Supposedly that's the case, but
Because
who knows?
Because most of them are physicists or engineers, which are applied physicists. And what's one of the most common things we say, Wayne?
What's that, Robert?
Let's store it because you never know when you might need
You
it.
need it again. Yeah, you don't throw anything. We're pack rats, in other
We're pack
words.
rats.
Yeah.
So,
But of course, the technology advances, so you don't go back and use what was developed in the 60s because we're well beyond that, right?
and what happens is somebody's going through the back of the warehouse to clean stuff out, and what happens is like me cleaning out a stock room one time, and I found an Altair computer, which for those who don't know, that was the first, what do you call it, desktop.
Is that the one they play Pong on?
No, this one just had little flip levers and everything
Oh,
that turned
okay.
switches on and off. But people found out ways to make the fan motors and everything play music by how they program those flip switches.
Right.
But there was no monitor, no keyboard to this thing. It was just a microcomputer.
Right.
It was the first.
Yeah.
And, your calculator.
So now you put it in a museum,
That exactly.
a technology museum, or you put it on eBay and try to get money for it.
Right.
One or the other, Anyways, but
Or
it's
if you're
a
a university physics department, you just put it on a shelf somewhere. You keep rolling it forward.
oh, there's a dig, Robert. There's a dig.
Yeah.
So it's not the optimal way to run a space program.
It is definitely not how to run a space program.
Especially when money counts, right? I mean, this stuff is expensive. We want to, and it's taxpayer money, so we want to spend the money wisely, as if it was our own money, right? And be
Now-
very careful, frugal on it.
You want to do that even when, as NASA's current budget is right now, less than 1% of the budget.
Yeah.
It is not the massive 10, 20, 30% a lot of people think it is. It is less than 1%.
Yes, but you want to set the example.
But you want to set the
You
example.
don't go to a meeting with NASA and order $10,000 worth of lobster from Maine.
We won't go there.
Sets a bad example,
Yes.
right? Be reasonable with the money. It's not ours. It's taxpayers' money. It's not
Right.
only ours.
So,
Now, speaking about going back to the moon, it's been a lot lately in the news about other countries like China, for example, wanting to go to the moon. And in the not too distant future, there'll probably be several more that will join that. And one of the things we've talked about for several decades now, because we know this time is coming, is what do we do with the early artifacts now that are on the moon itself? So all the equipment left over from the Apollo program, and even before that. So in this image you see on the right is from Apollo 12, where they're taking part of the Surveyor spacecraft and bringing it back to Earth to analyze it, to see how the lunar environment affected the equipment. In fact, the piece that they bring back actually had bacteria growing, had life form that was on the equipment. And that life form actually came from the Earth and actually survived for a certain period of time while it was on the moon in the vacuum of space.
yikes.
Yeah, and it was still alive when they brought it back to Earth. So that's amazing, from that. But it begs the question, and that's what this paper, you see the title page here, the abstract there on the bottom left, is wondering what should we do to preserve our history. So you can imagine this situation where some country X, let's say, and I don't mean SpaceX, I mean just some unknown country, I don't want to mention any names here.
Right.
They land at the Sea of Tranquility, walking distance from where Armstrong and Aldrin landed. In fact, you can see the descent stage is still on the lunar surface.
You've
And
seen that with MRO.
You can see the equipment that's left behind, and you can see, and if you were there, of course, you'd see all the footprints.
Right.
Who's to say that somebody who, let's say, is not too happy with the United States, doesn't take some kind of an object that smears the soil around and cover up every single footprint that was embedded in the lunar surface from the Apollo 11 landing,
Right.
just to destroy the history
And
of what happened, and then cart away the equipment that's left behind.
yep. And this is why if I were the chairman or whatever they call it for the UN, I'd be calling for a resolution that at least Apollo 11.
A UN resolution?
Yeah. At least Apollo 11.
Are you
site.
sure that people even pay attention to those
Probably
resolutions?
not. But it
Look
should
at-
be. Apollo 11 should be a World Heritage site.
It should be.
You know,
We got
the
UNESCO,
other, I'm not as concerned
United
about.
Nation, right?
Yeah.
World Heritage Sites.
Yeah.
But you wonder, is that enough? Right?
It's only as good as the paper it's written on and the people who want to adhere to it.
I mean, how many examples do we have of UN resolutions that have been totally ignored or violated
Yep.
because it was in the interest of some party who happened to be one of the permanent members higher up, and they
Yeah.
can do, it seems, at nausea what they like.
Or-
UN resolution doesn't mean anything.
Or, yeah, again, it has to mean something to the people who signed off on it.
Go look up the League
Yeah.
of Nations and find out what happened there.
Yeah.
Is it really too dissimilar from the UN that we have today?
Supposedly it is, but the UN has become a League of Nations. And it'd probably be better to just disband it.
As far as I'm concerned, like I said, disclaimer, our own personal opinion.
Yep.
It almost as if it's just a sounding board, a soapbox that you stand on from any country you want
Yep.
to vent your grievances, but nobody really cares. And in fact, a lot of times other member states don't even show up in the same room,
Yeah.
so they don't listen to you anyways. You
Right.
talk to nobody.
And that's what I mean. That's what happened with the League of Nations and why it eventually disbanded. The UN was actually chartered to be a stronger organization, but over time, the strength of that has been watered down.
Now, there are equipment from different countries that are on the moon. The United
Yep.
States, obviously, Russia, China,
India.
India, and European countries.
And even
In fact,
some-
even Israel, where they crash landing. You even talk about unsuccessful landing attempts.
Yeah.
That material. So we
Japan?
have several countries then have material. So what should we do with those sites? Should we form, whether it's under the UN umbrella or something else, some kind of a committee of nations who have landed things on the moon to say these particular areas, because of historical reasons, are, if you like, areas that are protected and that you need to avoid.
Right.
You can't disturb anything. We want to see the footprint that was made by Armstrong on July 20th, 1969. We want that preserved up until the point where maybe micrometeorites would disintegrate it.
Yeah.
But then, should we go to the moon and put up some type of structure surrounding the sites, like a bubble? You know what I'm saying? A material where micrometeoroids can't penetrate through and destroy so they essentially last
Yeah.
forever, billions of years type
Right.
of thing.
And the answer is, these are probably worthy things to be considered, but who's going to do it? Who's going to pay for it? Who's going to
The lunar,
agree to follow the dictates?
the Lunar Museum.
Absolutely. I
So
think it's a good idea.
Yeah, it would be nice if they do that.
It's kind of like, though, here on Earth, you can't call everything a World Heritage Site,
Yeah.
okay? But there are a few sites that should be recognized, and people just should not mess with them.
Yeah, for sure.
So, yeah,
So interesting. It's definitely time to do this
it's
discussion.
time to do it now
Yeah,
before we get to permanent lunar bases.
exactly. Okay, Robert. So there's something I talked about a while ago, especially the week that you weren't here, I believe,
Okay.
is there are the next catalog of the latest, greatest detections coming out very soon from the gravitational wave detectors. So this is the LIGO and Virgo. And
What is Kagra?
that's the one in Japan.
Oh, okay.
That came online a couple of years back, shortly after the first detection in 2015.
Okay.
So just to kind of familiarize people who maybe don't know the history of this too well, is way back, more than 100 years ago with the general theory of relativity from Einstein, which was late 1915 that he started making it known and eventually published. One of the predictions, and Einstein actually flip-flopped a little bit on this, is that there are these gravitational waves that would get released from sources, masses that are accelerating relative to each other. So think of like Jupiter orbiting the sun, for example.
Right.
And because Jupiter is accelerating, of course, the sun is also accelerating. It's orbiting the center of mass of the solar system, the barycenter, as we call it. There will be these undulations in space-time, one way to put it, that will get released from that source. And these undulations would consist of both of a stretching in one dimension of space and a squeezing together in the other dimension.
Yeah.
And these gravitational waves, as we call them, would propagate outwards at the speed of light. And they would get weaker as they spread out. The amplitude would go down. And an analogy there, a simple analogy, would be if you're on the other side of a lake from a speedboat and you're just laying back, let's say on a rubber tube or something, just enjoying the summer, and the water's really still, and then all of a sudden you feel a little bit up and down motion. Then you wake up and look off in the distance and you see that a boat had gone by recently. And of course it takes time for those waves to get you. But when the waves hit you, you're far enough away. You're not going to get the same amplitude as if you were like within a couple feet or a meter of the boat or something, right?
Right.
Those waves dissipate because of the friction of the motion of the water and so on and so forth. So you just get this gentle sort of motion by the time it reaches you on your side of the lake. So that's kind of what happens here with gravitational wave sources. They get weaker as they spread out from the source of these waves. And in 2015, we detected for the first time these gravitational waves. It was due to the merging of two black holes, what we call a binary system, where two black holes were orbiting around their center of mass, and they get closer and closer together as energy is released due to the emission of gravitational waves. So the separation gets smaller and smaller and smaller until essentially all of a sudden they merge together. And then there's a burst of gravitational waves that get emitted in the formation of now a single black hole in this case. And the single black hole that forms has a mass less than the sum of the individual masses of the two black holes.
And it's actually a significant loss.
Yeah. So, and for example, you could have a 50 solar mass black hole and a 60 solar mass black hole. When they merge, if you add those two numbers, that's 110 solar masses. One solar mass is just the mass of our sun, which is about 2 times 10 to the 30 kilograms for those who are interested. When the 60 and the 50 solar mass black holes merge, they don't form one that has a mass of 110 solar masses.
It's more like 97.
Or somewhere around there. So a lot of that mass that's missing has been turned into energy, which is where the gravitational waves come from.
Right.
Okay, and it takes a lot of mass, which means a lot of energy, because in some sense, you want to think of it this way, space is stiff.
I was going to comment
And
on
it
that.
takes a lot of energy to move space, to squeeze it and stretch it. So the one that was detected then in 2015, the very first one, was a confirmation then of the fact that these, number one, these gravitational waves exist, and that's ultimately a prediction from the general theory of relativity. So it shows that that theory is still consistent with observations.
Right.
In fact, there's never been an observation that's inconsistent with the general theory of relativity, but we know it breaks down at some point.
I was about to say, except at the quantum level.
Because of the quantum mechanics, the quantum level itself. And so far so good, which is amazing given all the technology. In fact, like the GPS system doesn't work without relativity, both special and general.
Yep.
And so we need all that information. And we see time and time again that people do lots of experiments or make lots of observations showing that they are totally consistent, the results, with the general theory of relativity and the special theory of relativity. Now, you might ask, well, how do we detect such a thing? This is the interesting part. By the time the average gravitational waves sweep by our location here on Earth, and what I mean by the average means if you think of all the different sources that would produce gravitational waves, what are their average distance from us? And they can be billions of light years away.
Right.
So by the time those waves reach us, they're very, very weak. So if we take some kind of a interesting, if you like, scientific analysis of what are the different sources of these gravitational waves, what would be the average wave that would sweep by the Earth, it would stretch or squeeze space on the order of like 1/10,000th the size of a proton. And we're talking about, can I use the word, astronomically small in this case?
Governmentally small.
Yeah.
Budgetarily small.
Length scales. So we're talking about something that's so tiny, the change in space is so small, and it would have absolutely no effect on you at all. You don't even realize it had passed through. And these things pass right through the Earth. Like there's nothing that stops them, because the space itself that's slightly changing in size. And so the hard part of doing this sort of detection was, how in the world do we come up with some type of experiment that could detect changes so small in the stretching or squeezing of space? Now, of course, some people might have suggested maybe back in the 60s or 70s, we'll never be able to do that. So it's just one of those things we'll never be able to test.
And they were wrong then.
But technology advances so much so, and humans are so smart. When you think about it, compare Neanderthals with us.
Right.
Look how much things have changed. And that's not a long period of time, really, given the history of the universe of nearly 14 billion years, right? Neanderthals were around a few 100,000 years ago.
Right.
So there's been a lot of development in our capacity to understand our environment, to use tools, to invent things. It's amazing when you actually think about it.
It is.
And that's such a small little sliver of the total age of the universe. That we've actually developed technology by 2015 that allows us to detect these tiny, subtle motions.
And what gets me is the technology was actually there. It was the detector that we needed. Because the technology being used is just a simple interferometer, which has been known since, what, the 1800s?
Yeah. Well, you think of Thomas Young, 1801, the
Right.
famous double slit experiment with light, and
Right.
showing that light is conclusively made up of waves or has wave-like properties.
And I think we've said it before, but all an interferometer is we use a beam splitter to send the same beam down two different paths. So some of the energy goes one way, some of it has been off at a 90-degree angle another way. Then it's reflected back and recombined. And if they're in phase, if they're meeting crest to crest, trough to trough, we get a bright spot. If they're meeting crest to trough, they negate each other and we get a dark spot. And to kind of give you just on a real world that you can see, I can set one up in one of our labs and show you that just a gentle breath will actually send those bright and dark spots to wavering. So in other words, it can detect that you change the air density by a gentle breath. You know, so these things are really sensitive, but what we needed was a detector that could detect this interference pattern on that narrow a scale.
Well, the biggest stumbling block in the development, why it took to 2015, is to isolate the equipment from the Earth.
Because, like I said, your breath will change.
So any type of tremors, 18-wheelers driving by on the nearby interstate would set off the detector, all these kind of things. So you have to isolate it as much as possible from earthly existence.
And then the other thing you really need is that second one coming online at the same time.
Yeah, so when this discovery was made in 2015, it was first detected in LIGO, the Light Interferometer Gravitational Wave Observatory in Louisiana.
Yep.
And then a fraction of a second later, it set off the detector in Washington State.
Right.
And we have a rough idea of the direction in which the gravitational wave was coming from, and the time delay from Louisiana to Washington State is exactly what you would expect if the signal traveled at the speed of light.
Right. So it was the same signal at exactly the time you would expect for it to travel at the speed of light. So it was the same.
So it wasn't local. It had
Right.
to be something else. And of course, since that time in 2015, we've detected hundreds of these sources. And so technology doesn't stand still, as we know. We keep advancing, keep advancing. So there are times when the equipment, now there's more than 2 detectors, there's now 3, and there are other ones that are coming online, one in India, and so on and so forth. And there's even talk of putting detectors out in space, the LISA mission, and so on and so forth, to get away from the Earth altogether, so we don't have to worry about that influence, terrestrial influence. But the thing is that the technology advances, what do? Well, you run your experiment for a while, and the first run was 18 weeks, as you see here in this slide. This is run 1. Then you shut everything down, do the changes to the equipment to make it more sensitive, and then you run it again, and that second run was for 38 weeks. Then you just repeat, rinse and repeat. Shut her down, do the adjustments that you need to do to make it even more sensitive, then run it again, and so the third run was 47 weeks. And then finally, you do the same thing, which is the latest data now that's going to be released, all of it very soon, is run number 4. And this is 90 weeks worth of observation.
Right.
Now, on the slide that you see here on the vertical axis is distance in billions of light years, okay? And then you see dots that are color-coded. Some of them are color-coded depending on the strength, okay? And there's even the size of the dots is related to the mass of the objects, the progenitor, what created the gravitational wave, in solar units. So we see some of them are up to 200 times the mass of our sun. So they would be merging black holes, or even black holes merging with neutron stars. Now, or even neutron stars merging with neutron stars. And the number of sources we have are on the order of several hundred. And notice that on the far right of the slide, and for run number 4, the latest run, you have a lot of these sort of just circles everywhere, and they're unreleased data.
Yes.
So they're still holding the catalog to themselves, the people who are involved in the project, which is how it goes, right? You do the analysis, then you make it public so everybody sees it.
Right.
The people pay for it. Well, a lot of it's taxpayer money, but the people who spend all their blood, sweat, and tears on this project should get access to the data first and start publishing their papers and so on. And so eventually all of that unreleased data will be released. But at least it gives us an idea of how far away the sources are.
Right.
Because they do plot those data points, and notice they go upwards to about 10 billion light years away.
I was noticing that. Yeah.
Now you might wonder, how do you know the distance? And here's how you do it. How do you know, for example, that it's two black holes? And the example I gave earlier was 50 solar masses and 60 solar masses. How the heck could you determine that from the gravitational waves? Well, it turns out the actual waves that you detect, the waveform as we call it, depends on what actually produces the waves and how far away they are from us. Because it's the simple analogy I use with, sitting on the inner tube on a lake near the shore, and then a speedboat goes by on the other side of the lake, and eventually the waves reach you, but they're very low amplitude, the height of the waves. So we know that if the amplitude is low, and how low they are, given what created the waves to begin with, how far away that progenitor, that source should be.
Right.
That's how it ties together. So literally what happened is people use supercomputers, and they run through all of these sort of cases. For example, what would happen if I had a 20 solar mass black hole that merged with a 50 solar mass black hole, and we're located 1 billion light years away from the Earth? What would that waveform look like? And you'd run numerical relativity codes, so computer codes, that would run on supercomputers so you can generate as fast as you can, and you get the waveform from that. Then you put that aside into a library, and then you run again on different case, different distances. And you do that over and over, and you build up all of these libraries of all these different waveforms. Then when you get a detection, you just have the computer to take the observation and go through all of the libraries that we have of all these different possibilities in terms of the progenitor and how far away it is to see which one provides the best match. And that's how we can interpret both the masses of the object that created the waves and how far away they are.
It's oddly enough very similar to what we were discussing about spectroscopy last week, how the width of the lines, the shape of the lines, all tell us information about what's going on with the source of the light. All of these shapes of these waveforms encode what produced them. So we can figure it out.
I wonder if we ever discovered life somewhere else. One of the signatures we could use of whether or not it's an advanced life is whether or not they have developed the technology to detect gravitational waves.
There's something to that.
I mean, gravitational waves has opened up a new window of the universe. And here's an example why I say that. In most things in astronomy, you detect from electromagnetic radiation.
Right.
Whether it's optical light, infrared, ultraviolet, X-rays, you name it. But think of this case. You have two black holes. One's 100 solar mass. One's 200 solar mass. They merge. They create a burst of gravitational waves. These two objects, before they merged, are at a distance of 50 million light years from the Earth. They produce a burst of gravitational waves. Those waves pass through the Earth and continue going in that direction, right? They go in all different directions, of course. But if there is nothing around those black holes, there's no other matter at all, they are completely isolated, there is no electromagnetic signature that gets released in that merging process.
Right.
In other words, we would not have a clue that this event happened.
Yep.
We would be totally then, if you like, isolated from any of these objects that merged.
Right.
Because we're not sensitive to the gravitational waves, and that's the only thing, the only signature that we have that would signify that that event happened. So that's why I say it opens up a whole new window in the study of our universe.
And John Porton is pointing out not all spectrum are equal, and that is 100% correct. This is why you calibrate it against the terrestrial source, like a neon lamp. You calibrate it against Altair or Regulus or something that's been observed for who knows how long. And then you calibrate, you take your spectra of your target, and hopefully you ran a good run.
Or
But when you start comparing those calibration spectra to it, that's how you know, oops.
or you get into a situation that we presently find ourselves with that ringed object we discovered,
Right.
where our spectrum has so low of a signal to noise, we're having a lot of trouble trying to squeeze any information out of it, unfortunately.
So not all spectra are equal.
Yeah,
You
so
are
Extra Buller,
100%
we're not
correct.
ready to come on your show to tell everybody what we found yet.
Yeah.
Because of that, even though we got a large amount of observing time on a very large telescope, this object is really giving us a lot of
dim.
trouble.
It was really dim.
So spectra are not all the same, for
Yeah,
sure,
for sure.
for many reasons.
All
Now,
right.
Robert, I thought you'd be interested in this study. Mm-hmm. So this study is the detection, once again, because we've had sort of a detection like this before,
Yeah.
of a planet orbiting two stars,
Yes.
not just a single star.
Yep.
And that's from Star Wars.
Star Wars and
What's a
several
classic example? You remember the names in the Star Wars?
Oh, Tatooine?
Yes.
Yeah.
So we do have, we found it once before, but we see it here once again.
Holy cow. I just read the slide myself. The stars are only 0.54 and 0.4 solar masses, and it's a Saturn-Mass planet?
Yeah.
That size planet there shouldn't have been enough material to form that size of planet around
Well,
these
you
guys.
better tell these
Holy
guys. You
cow.
better tell them they shouldn't exist. See what they say.
Oh, no. I mean, come on. Planets around a binary shouldn't exist because the gravitational turbulence should be enough to rip them apart.
Robert, you're so solar system centric, man.
Yeah, well,
Get in with the modern times here.
the modern times here, wherever we've looked, we tend to find planets. Planets are common.
And the planets are not like our planetary
Oh, no.
system at all.
So, we've now found planets that we thought couldn't exist. So planets around individual stars in a binary. Planets around, like this case, the binary, both stars. We found planets going perpendicular, essentially, to the orbital plane of the two stars. Holy cow. How does this happen?
You ask astronomers back like in 1980s to
this
say
is cool stuff, by the way.
someday if we find another solar system, planets around another star, what do you think it would be like? Well, they'll probably have 4 rocky planets and probably, at the inner
remember
part of the
those.
solar system. And then you had probably 4 gas giants that are in the outer part with
Yeah.
icy moons and stuff. In other words, you'd have the same solar system we live in. No!
And they'd all be around G-class stars, and it's like, no.
That's what
We are
happens when you
finding them
form
everywhere.
That's what happens when you form opinions and ideas based on a sample size of.
one. Yeah. But, don't get me wrong, folks. This is so cool. This is why I got into planet formation, is what I wanted to study.
Now, Robert, if someday you decide you'd like to have this exotic vacation and go to this system, notice how far away it is from us.
That's only 22,000 light years. 23, give or take. If we're going 0.9 C, I think I can live long enough to get there.
But it is an amazing discovery. It's
It
cool.
is. Oh man, this is so cool.
And it just makes you wonder how many other really bizarre systems exist
I
just
hope
in our
I'm alive
galaxy.
to find out. Oh, this is great.
Can you live to be 1,000 years old? Look at all the discoveries we're going to miss.
I hope
you
so.
see?
Man, this is great stuff.
Now, speaking about that, how do you like this study?
Mass transferring binary. Wow.
2 brown dwarfs about 1,000 light years away, so it's a lot closer.
A lot closer.
So maybe you can go on vacation
Yeah.
where we actually find mass transferring from one to the other. In fact, they are close enough, right? So they're each other's within that Roche lobe, as we say,
Yeah.
where you can actually pull material off of
one
onto the other. So the more massive one probably pulls off material from the least massive one. In fact, the mass transfer could happen to a degree. Actually, before I say that, let's define what a brown dwarf is all about. Do you want to do the...
Sure. Bottom line, if gravity infall is the only way to form a star, there is a limit to how low a mass the star can be. This is called the Jeans limit, if I remember correctly. No.
And why is there a limit? Because you need to do what to be a star?
I'm missing something.
Hydrogen fusion.
Hydrogen fusion, yes.
Right. So you need the temperature,
that's right.
right?
So
a 10 million Kelvin
Yeah.
minimum temperature for sustained
For
fusion
sustained fusion.
of hydrogen and helium. That requires a mass of 8% of the sun's mass.
There you go.
0.08 solar masses.
Right. Anything less than that, it might undergo fusion, but it'll be deuterium or lithium
Yes.
fusion, which is not stable.
Right.
So 0.08 solar mass is the smallest star you can have. So that's
Small as in mass, you're talking about.
Yes.
Not size.
Yeah, not size.
Yeah. The least
so
massive star.
anything below that, but above about 20 times the mass of
Above-
Jupiter,
Yeah, it's planetary scale.
is called a brown dwarf.
Right.
And so that's what these are. The bottom line, they're failed stars.
Yes. So in this situation, if we take enough mass and
Oh, wait. It could ignite.
yes, that's what I'm getting at. You could transfer enough mass from one brown dwarf to the other to the point where you push its mass over the 0.08 solar mass limit, and that object would ignite in its core hydrogen fusion and become a main
star.
sequence star.
That
A
would be cool.
star is born.
That would be cool to see.
That'd be amazing.
That would be amazing to see too. Heck yeah.
And to give people a sort of sense of scale in terms of the size of these objects, this is a good slide for that. We see on the far left the sun to the scale. Then we see a low mass star to the right of that. And then we see typical brown dwarf size. And then we see the size of, for example, Jupiter, the largest planet in our own solar system. And then on the far right, we have Earth to scale. So the Earth, compared to Jupiter, you take about 109 Earths strung like pearls on a string to go from one side of Jupiter to the other. So that's how large Jupiter is compared to the Earth. But look how large Jupiter is compared to our sun. It's really tiny in that sense, right? But it is relatively close to the size of a brown dwarf. And in fact, some astronomers who study brown dwarfs, they have a hard time coming up with a standard definition of what's a brown dwarf and what's a planet,
Right.
because they can be extremely similar. And some of the brown dwarfs can have, surface temperatures that are sort of the type of temperatures we find on Jupiter on its outer atmosphere. So there's a lot. It's a continuum, right? And it makes sense, right? Start with the very massive objects, and work your way down. So let's just start with stars. You have really massive stars, right? Many, some would fill up the inside of Jupiter's orbit in our solar system if they were where the sun is. And you make your way down and get smaller and smaller and smaller. Then eventually you get to the very low mass stars, 8% of the sun's mass. Then you're down into brown dwarf size things. Then you get smaller, smaller, smaller. Then you're into planetary things. And then you get smaller, smaller. Then you're into like moon-like sizes.
Yep.
Right? Then you get smaller and smaller. Then you're in asteroid such sizes. Then you go smaller than that, and you're kind of in the typical meteorite type of sizes. And then you get smaller, you're into like boulders. Then you're into stones and pebbles.
And
then
dust.
dust, and eventually into dust grains.
Yep.
So you get the whole continuum. There's nothing in physics that says thou shalt not create an object that has a mass less than some value.
Right.
Right? There's nothing that forbids that. So you'd expect the whole continuum of these things. And prior to the mid-90s, we never knew the existence of a single brown dwarf.
Right.
And yet in stellar nurseries, there should be these objects that formed but didn't have enough mass to become a real star, that they should exist as brown dwarfs. And nobody could find them for a long period of time.
Yep.
And people started to get worried. Is there some fundamental law of physics that we're missing in all this that prevents those objects from forming?
Yeah.
And it turns out the answer is no. We just didn't know how to look the right way.
Right.
And once we found the first brown dwarf, then it was easy there
Then
for
it's
us.
easy.
Now we've discovered thousands of these things.
Yep. So, and they're right where you'd think they were. They're in stellar nurseries, right there beside all the rest. So,
Now, when we look at really small things, some of the things would include comets.
comets.
So this is an interesting paper that just came out recently describing the breakup of Comet C 2025 K1 Atlas. Now, we had mentioned this in a previous podcast way back when.
Yeah.
But here's like the first scientific paper, one of them that's come out, that describes in detail the breaking up of the comet. So the comet actually broke up after it flew by the sun. So we have this comet coming up, 2026 maps,
Yeah.
and that's going to pass by the sun that is make its closest approach around April the 4th. And we're hoping that if it doesn't break up and it hangs together, it could potentially be an extremely bright comet in the western sky, low to the horizon from where we're located, right after sunset.
Right.
And if it gets bright enough, it should be an easy target to see in the sky. In fact, you may even see with just your eyes. You won't need binoculars or telescopes or anything like that.
Yep.
We'll see. Now, this particular comet that the study's based on did break up, but after it went by the sun, it was
Which
later
is a
on.
frequent thing.
Which is a frequent thing. And it was not expected at the time, and people had asked, you proposed time to use observatories like the Hubble Space Telescope. And so they actually acquired images of the comet while it was in the process of breaking up. So this is sort of in November sort of time frame of 2025, a few months back.
It reminds me a lot of Comet Shoemaker-Levy 9 when it was passing close to Jupiter and
Right.
did the same
Yeah.
trick because
Yeah.
it got too close to Jupiter.
That just tells you the constituency of comets, like its intrinsic structure, what it's
Yep.
made up, its tensile strength. And I'm sure there's a variation in that.
Mm-hmm.
But, Fred Whipple, for example, he was a famous comet astronomer, scientist, and he made the description that it were like dirty snowballs, is what he called comets. In some sense, that is actually pretty accurate of
Yep.
what we think comets are like. So,
And what we found comets to be like when we've sent our probes to them. So
yeah, so very, very interesting in that sense. Another very interesting thing, this study that was just released a couple days ago is based on the fact that using the Gaia data, DR3, now Gaia was this mission that was launched by the European Space Agency. Primary goal was to measure stellar parallax of as many stars as it could. And stellar parallax is one of these measurements where you're essentially using old surveyor method or trigonometry to estimate the distance to a star. So the object here is you observe some star from either side of Earth's orbit. So let's say in June or July you would observe, then you observe it again in January, so that the separation between those two observation points is the diameter of Earth's orbit, about 2 astronomical units, as we would say. And if you looked at a nearby star relative to much further background stars, you would see a shift in position of that nearby star, potentially. It's like putting your finger in front of your nose a certain distance away, look at it with one eye, and notice where it is relative to the background, then look at it with the other eye and try to go back and forth, and you'll see the shift back and forth of your finger. That shift is related to how far away the finger is from the line between your eyes and how far your eyes are spaced out from each other.
right.
So by trigonometry, if you could measure that shift, you could estimate the distance to your finger. In other words, in this way, you can measure the distance to the star.
To the star.
And so the spacecraft has provided data for on the order of like 2 billion or more stars, mostly in our Milky Way, measuring their distances using this parallax technique. But they released the data. The spacecraft finished its job over a year ago. It was a year ago in January. But all the data hasn't been released yet. Once again, scientists, have the right to use the data and do their analysis
They can ask for
first.
extensions and
Yes,
things like
before
that.
they release it to the public. So this study is based on the 3rd data release, and there's going to be at least probably 1, if not 2 more,
Right.
before it's all released. And what they discovered is through the measurement of the distances to objects and their motion, their proper motion, is they found 87 globular clusters in our Milky Way, which have these long tidal tails coming from it, streams of stars.
So they're being ripped apart by the Milky Way.
Yeah, by the gravitational and tidal forces. So in that sense, the globular clusters are evaporating, if you want to
Right.
think of it in that terms. For 87 of them, now there's roughly about 200 or so globular clusters in the Milky Way. So I would speculate if we had the good enough measurements, all of them are probably undergoing this sort of slow evaporation, destruction, if you like.
I would in fact bet that we've always noticed that the cores are blue with heavy hot stars.
Blue stragglers.
Right.
yes.
And then the outsides were more low mass red stars. So it's kind of like things settling in. So I'm willing to bet those are probably lower mass stars that are in these tails.
Yeah, you'd have mass segregation, as we
Yeah.
call it, separation of the mass. In fact, after a while, you'd expect probably just the cores would survive because they can hold itself together gravitationally more than what the gravitational tidal field can rip them apart from their passage around the
And
Milky Way.
that's where I was going with
Yeah.
it. But yeah.
Very interesting study for sure. Now, next slide, Robert.
Yeah.
You heard of ET phoned home?
Okay.
Well, this spacecraft actually phoned home.
Oh, okay.
This spacecraft is built by the European Space Agency. It was designed to make artificial eclipses of the sun.
Okay.
And you can see there on the slide on the right, it actually was separated into two pieces, separated by 150 meters. That was the goal here. And what happens is one part of the spacecraft blocks the light coming from the sun.
From the photosphere.
From the photosphere.
Yeah.
Where the other spacecraft then images the corona. That's the part of the sun you see during a total solar eclipse. So for those of you that were lucky enough to have seen a total solar eclipse in the past, like the one in August of 2017, the other one April of 25, I think, 24.
24.
Yeah, 2024. You know what I'm talking about. You see that outer part, the outer corona. And so why wait for total solar eclipses to occur if you can generate them all the time?
Right.
And you can do that in space and not worry about the Earth's atmosphere affecting things. So that was the goal of this spacecraft. But unfortunately, a little over a month ago, they lost contact with the spacecraft. So all communication, in fact, they probably thought it was over with, the mission was done. And that's not a good thing. Of course, these missions cost a lot of money, and it just got going, really. And so it was a shame, right?
Absolutely.
But unfortunately, just recently, the spacecraft phoned home and established communication with the Earth.
Nice.
So now they have to reboot the chronograph, the instruments and stuff, because were put automatically in safe mode when they lost communications with the Earth, and try to get this vehicle now producing science.
Yep.
That's the goal. So it's amazing. Sometimes things happen unexpectedly, and this was certainly unexpected. Nobody thought that would.
They were probably closing.
Yeah. So, and you can see here how it kind of works. There's the orbit that it's on, a highly elliptical orbit. You have one part of the spacecraft sort of on the lower right blocking the view, that is, of the sun, making a shadow, essentially, on the spacecraft that has the camera, the detector. So to take an image of the sun's corona, you got to block, as we mentioned, that really bright photosphere. So that's essentially what's setting up here. So it's a very nice design.
Yeah.
And it makes...
And it shows we might be able to put together a space interferometer, because that spacing is pretty
precise.
precise.
And the other thing to note is we get a lot of information during a total solar eclipse here on the Earth by analyzing what is the structure and shape of the corona.
Right.
The corona changes shape. It's very dynamic all the time, and that's influenced by solar activity, for one thing.
Yep.
So we can have a more detailed, hopefully, understanding of the connection between the shape of the corona and what's actually going on with the sun at that particular moment in time. So it's definitely going to provide us additional information.
Cool.
Now, we're essentially at the end of the podcast, so maybe we should do a little bit of an advertisement for what's coming up. So if we want to go to that slide. Yeah. So here's the special guest that I alluded to then that's going to appear, hopefully, knock on wood. You hear that knock? I'm hopeful. And this is on April the 7th. And the person who's destined or said that they would appear is Dr. Andrew Knoll from Harvard University. He is, as the slide says, an award-winning paleontologist and author of several books. Okay? And he's going to be with Robert and I on that date. So we're looking forward to talking with him.
Well, not in person, but we'll have him on
We'll have him on Zoom. He'll be a guest, but we're looking forward to talking with him. And I'm sure he'll have lots of things to talk about. He's also been part of the Mars Exploration Rover mission, the Spirit and Opportunity. He was on that for like 20 years on the science team.
Probably looking for archaeological, paleontological science.
Yeah, applying what he learned here, looking at Earth, and applying that to the Martian environment. And so he'll have a lot of interesting things to say. And so we're really looking forward to the appearance of Dr. Knoll. So that'll be on April the 7th. And hopefully all of you will be able to join us and send in your comments and questions at that time as well. Our next podcast will be a week from today. So this is March
30th?
The 31st.
31st.
End of the month.
End of the month, yeah.
So there goes March. How fast was that? You know? And then the one after that will be April the 7th. So if you like to get involved in this kind of research, whether it's in a STEM field or in the arts, whatever, come to places like the University of
North Dakota.
And you yourself can become an award-winning author and paleontologist or astronomer or physicist or geologist or biologist or chemist or an English professor or you name it, right? We got or aviation. I mean, there's so many programs that we have here at the university. So hopefully
Right.
there's something that actually would be exciting for you to partake in.
Absolutely. And a lot of programs are online.
And a lot of programs are both online and on campus. So not in the day now do you have to actually physically come to campus. You could be sitting in a hut in Tahiti, enjoying the life and retirement, and decide, I like to take that class that I was always wanting to take back when I got my degree several decades ago at the University of North Dakota. I had such a beautiful career because of that degree. Let me take that interesting course. You see?
There you go.
As long as you have internet, have access.
As long as you have the internet.
Yeah, you have access for that. Now, at the end of every podcast, we always leave you with a quote. Now, the quote is related. If Robert wants to show this quickly, the slide from the Large Hadron Collider story
Okay.
that we ran out of time to really get to.
That's that slide.
Yeah,
Whoops, that slide.
That one. There's the one. So you might wonder, what's the Large Hadron Collider up to these days? Its biggest discovery was the Higgs boson, and that was a long time ago now.
Right.
And one of the things that it discovered recently was the appearance of a particle that's similar to a proton. It weighs a lot more than a proton, but instead of being made up of two up quarks and a down quark, this particular object is actually made up of heavy quarks, and in particular, two charm quarks and a down quark.
So it's charmed matter.
Yeah, so it's a double charmed particle, as we like to say. So this has not been seen before. It's highly unstable. These things decay in a fraction of a fraction of a fraction of the blink of an eye. But we have the technology. We were speaking about detecting gravitational waves before. We have the technology to detect these particles. It's amazing when you think of.
Yep. Because
And
it
so-
leaves a chain of decay products.
And a lot of our work has been done through the fact that we build these so-called particle colliders. We take particles and smash them into each other. And the person that came up with the first collider, the first cyclotron, as we say, was Ernest Lawrence. And he actually won the Nobel Prize in Physics back in 1939 for the construction of the first particle collider. And the LHC is sort of the latest generation of this long family of particle colliders that people have built over the years.
Right.
So I'm going to read a quote from Ernest Lawrence. And here's the quote. The day when the scientists, no matter how devoted, may make significant progress alone and without material help is past. This fact is most self-evident in our work. Instead of an attic with a few test tubes, bits of wire, and odds and ends, the attack on the atomic nucleus has required the development and construction of great instruments on an engineering scale. And that's
he
exactly
wasn't wrong. That's exactly what it is.
it is. Now, if you like this podcast, please remember to give us a thumbs up, subscribe if you haven't subscribed, and thank you very much for watching.
Y'all have a great day.